Hey guys, welcome back to another lecture video for Chem 115. Before we start on the next topic, I want to go back to this last problem that we worked on in the previous lecture video. And I just wanted to clarify some things that I forgot to clarify when I was making the last lecture video. And so this reaction that we're looking at right here is an irreversible reaction, right? And so for irreversible reactions, we know that we can't use all of the amount of energy that was produced from this irreversible reaction to commit it specifically for work. In reality, for irreversible reactions, some amount of the total energy available to do work is going to be lost as heat. Okay? And so when I did the calculations at the very end, I mentioned that this value right here that we calculated would represent the maximum amount of energy that would be released from the reaction. And so this negative 358.5 kilojoules per mole is the total amount of energy that was released from the reaction. And if this was a reversible reaction, not an irreversible one, then the relationship, that W max is equal to delta G still holds true, right? So this is the reason why the value itself doesn't change. And so the only thing that does change is the sign, and that's what I want to clarify. Why does the sign change between the maximum amount of free energy that was released from the reaction to positive 358.5 when we're talking about the maximum amount of work theoretically possible that could be done if this reaction is a reversible reaction. And so I want you guys to imagine this system here. So here we have this like movable, we have this movable piston, and it's connected to like this lever. And basically what's going to happen is that if this lever arm, whatever thing, rotates, then it's going to push this rock off the table. And so that action in itself is some type of work, right? So we're coupling a spontaneous process to something that's non-spontaneous. Now, the spontaneous process in this scenario would be the combustion of oxalic acid, right? So here, if we have a combustion reaction occurring, and I'm representing that kind of like as an explosion, the lid is going to move upwards, which is going to allow this arm, if you will, to push this rock off the ledge. And that would be the work that this example is performing. And so if you can imagine, if this is all a reversible process, and we know that it is not, it is irreversible. If this was a reversible process, then the amount of energy that was released from the combustion reaction, all of that energy is going to go into, maybe I should do this in a different color, all of the energy is going to go to making this piston go up. Okay, so therefore, all of the energy is going to be committed for work. Now, when you have a positive sign for work, this positive sign means that you are work is being performed on the system. Okay. And so in this case, the work that we're talking about is pushing this rock off the ledge. And so the reason why this value is positive is because the system is no longer the combustion reaction. The system is going to be the rock. So the Gibbs free energy, this free energy, is talking about the system being the combustion reaction. However, when we're talking about the performance of work, the system now becomes the rock, and work is going to be performed on it so that it can fall off the ledge. And that's why that value is positive. And so if we maintained a negative value, then that's telling us that work is being performed by the system, which in this case, it's under different perspectives. And so the maximum amount of work is it's typically a positive value that we want to report because we're indicating how much work in terms of energy units is going to be performed on the system. All right, so the next topic that I'm going to discuss, actually this is going to be the last topic that I'm going to be discussing for thermodynamics, is looking at Gibbs free energy and equilibrium. We did look at equilibrium a little bit in the previous lecture video, but that was in the perspective of work and melting point temperature and boiling point temperature. But what if we want to just broaden this to general chemical equations? What is the relationship between the Gibbs free energy and when the system is at equilibrium, or the chemical reaction is at equilibrium? So we're going to go ahead and go through some concepts, some examples, and that will just tie up the chapter. Okay. And so before we talk about the calculations, we need to understand the relationship between Gibbs free energy, which is delta G, and that of the equilibrium constant. And so we've been, working with equilibrium constants for quite some time this semester. And so just to quickly review, if your equilibrium constant is far, far greater than 1, what does that tell you about the reaction system? It tells you that at equilibrium, the product side is going to be much more favored than the reactants. And if your delta G, if the change in Gibbs free energy is less than 0, we know that value is going to be negative, and it's communicating to us as readers that the forward reaction, the production of the products, is going to be spontaneous. Okay? So there are two concepts that we're now trying to merge together to create, this bigger picture of what's happening in a chemical reaction. And so once again, this K value, if it's far, far greater than 1, we know that the equilibrium is going to favor the products. And since we're favoring the production of the products, it would make sense that the forward reaction is spontaneous. Okay? Now, it doesn't make sense if you have conflicting results. And so if your equilibrium constant is far, far greater than 1, yet your delta G is positive, you're telling me that at equilibrium it favors the production of the products, but it's a non-spontaneous reaction. Okay? And so typically we want those concepts to align. Okay? And so what we're going to do is we're going to discuss how the free energy is related to equilibrium in terms of a diagram. Okay, so we're going to look at the concept first. And so looking at this diagram, we get something that looks like this, where the free energy is going to be on the y-axis and the course of the chemical reaction is going to be on the x-axis. And on this x-axis, we have the reactants, in this case substance A, that's going to be found on the left-hand side, bottom left corner of this graph. And we have substance B on the opposite end of that x-axis. and that's going to represent the product. And so if your K value is far, far greater than 1, and if the change in Gibbs free energy is negative or less than 0, then this is the expected free energy diagram that one would be expected to see if you were to perform an experiment on this. And so let's go ahead and look at the parts. On the left-hand side here we have the free energy under standard conditions of reactant A. And notice that it's much higher, right? So the reactants has a higher potential energy, or has a higher amount of free energy compared to that of the products, which in this case is B. And so I want you guys to notice that as we're going from left to right, our line is going to go downward. And so our slope is negative. And so since our slope is negative, that's representing this spontaneous process, which kind of aligns with the idea of K is far, far greater than 1. In other words, at equilibrium, there should be more products than reactants. And so the process of going from reactants to products is going to be spontaneous, and it's going to be represented by this negative slope. That's why we see this line going down. Now, when it hits the bottom of this hill, if you will, or bottom of this valley, this is when the slope is equal to 0. And so when the slope is equal to 0, this is where your equilibrium will lie. Okay. And notice, if I kind of zoom out, the equilibrium lies closer to that of the products, which makes sense because our K value is far, far greater than 1. Okay. And so this point right here represents the relative mixture of product to reactant. And this equilibrium concentration of product to reactant is something that we've calculated many times in past chapters. And so looking at the right-hand side, here we have the products, and notice that we have a negative slope going down. In other words, it's going to be spontaneous for some of the products, not all, to produce some reactants. But once it hits this, once it hits the bottom part of that valley, if you will, that's when the equilibrium, that's when the mixture is going to be at an equilibrium. Okay. Now, if you were to think about climbing up the hill, right? In other words, I'm going to go ahead and erase this real quick. Good enough. And so, in other words, if you're at equilibrium and you want to get back to the reactants, notice that the slope from the hill going to the reactants is going to be positive. And so, since the y-axis is representing G, or free energy, if we have a positive slope, that's going to represent a positive value for G. Therefore, it would be a non-spontaneous reaction. Okay. So hopefully that made sense. Okay. Okay. And so right now we're just focusing on following the path down the hill, because that'll give us a negative slope, which is going to represent negative G, okay? Or free energy. And we know that if the value is negative, then it's going to be a spontaneous process. Now, another thing that we can do is we can calculate the change in Gibbs free energy by looking at where the energy, the free energy of the reactants lie. And we can go ahead and look at where the free energy of the products lie. Okay. And so the difference between these two is going to give us the change in Gibbs free energy. Okay. And so since the Gibbs free energy of the products is less than that of the reactants, our change in Gibbs free energy is going to be negative, which once again highlights the point that it's going to be a spontaneous reaction in the forward direction. Okay. All right, and so if you guys didn't catch why the value of G is negative, or this specific point, just think of 2 points, or just think of two numbers. One number is higher than the other. So the higher number is going to go to the reactants. The lower number is going to go to the products. And if you subtract a low number minus a high number, you're going to get a negative value. And that's how I got that negative delta G. Okay. All right, so the take-home message is the position of equilibrium is going to lie in favor of the products, which once again highlights the point that K is going to be far, far greater than 1. And so since the value of delta G is negative, the reaction is going to be a spontaneous process in favor of the production of the products. Okay. And so we're going to go ahead and take a look at this graph once again in the opposite direction. And so here in this case, K, the equilibrium constant, is going to be far, far less than 1. And if the equilibrium is far, far less than 1, we know that at equilibrium, the reactants is more favored. In other words, if Kc or Kp or any K value is far, far less than 1, the equilibrium concentration for the reactants should be much, much higher than the equilibrium concentration of the products. And that's something that you guys have calculated many times over in prior chapters. And so I'm going to go ahead and kind of add in and layer this concept with that of delta G. And so here in this case, when K is far, far less than 1, the Gibbs free energy, the change in Gibbs free energy is going to be positive, meaning that it's going to be non-spontaneous in the forward direction. Now, for looking at the little intricacies of what's happening in this graph, once again, the y-axis is representing the free energy. And so this is going to be the free energy of the reactants, reactant A. Okay. And this is going to be the free energy of reactant B. Or, I'm sorry, not reactant B. This is going to be the product, right? So B is going to be our product. And once again, at the x-axis is going to represent the progress of the reaction, the conversion of reactants to products. And so if you guys are looking at this free energy diagram with respect to equilibrium, let's go ahead and follow the lines, and we're going to follow the lines such that we're focused on the lowest points of the graph. And so here, starting from the right-hand side, notice that we have a negative slope, here we have a negative slope in the conversion of products to reactants. And so that negative slope tells us that the reverse reaction is spontaneous. Okay. Now, if I were to erase all of these blue markings, and if I were to go in reverse, I'm going to switch the sign of the arrow. For example, if I'm going up the hill towards the products, right? So B is the products. I want you guys to note that the slope is positive. And so if the slope is positive with respect to Gibbs free energy, then that means that the reaction is non-spontaneous in the forward direction. Okay. All right, and so hopefully you guys can see the interplay between, spontaneity and Gibbs free energy. So I'm just going to go ahead and redraw those blue arrows going down to represent a negative slope, or negative G, reminding us that the reverse reaction is spontaneous, while the forward reaction is non-spontaneous. And so when you guys get to this point right here, where the slope is equal to 0, this is where your equilibrium is going to lie. So notice that in this case, the equilibrium lies closer to that of the reactants than the products. Okay. And if you want to calculate the change in Gibbs free energy, I'll just do this in a different color. You can go ahead and determine the free energy of the reactants and subtract that from the value of the free energy of the products. And so basically, if I were to take products minus reactants, in this case, I'll just go ahead and write it down at the bottom. So in this case, GB, which is the products, notice that it's much higher than GA, right? So this guy is much higher than this guy. So products is greater than reactants. And so if you were to take the difference between those two values, so we have a high value minus a low value. So for example, 10 minus 5, that's going to give you a positive number. And so overall, we get a positive delta G, which tells us that the forward reaction is non-spontaneous. So this implies that the reverse reaction is spontaneous. And so the same thing can be said with this graph, like they're opposites of each other. So if the forward reaction is spontaneous, then the reverse reaction is non-spontaneous. All right. And so let's go ahead and take a look at the last case, the last scenario. which is when the equilibrium constant is equal to 1 and the change in Gibbs free energy is equal to 0. And so if you guys recall, when k is equal to 1, this system is under dynamic equilibrium. Where neither reactants or products is favored at equilibrium. And so that means that if you were to calculate the equilibrium concentration through the ICE table, et cetera, when k is equal to 1, those values, the equilibrium concentration of reactants and products, should be roughly the same. Okay. And so when we're looking at the thermodynamic quantity, change in Gibbs free energy, that's going to represent, that value is going to be 0. Okay? And we talked about the implications of delta G being 0 in other scenarios in the last lecture video. And so we can understand why delta G is 0 by once again looking at this free energy diagram, where the y-axis is representing the free energy and the x-axis is representing the progress of the reaction. So if you look at the level between G and A, or GA and GB, or the reactants and products, I'll go ahead and put this in a different color. Okay. So notice that they're approximately the same. And so therefore, if you were to take the difference between GB minus GA, then that's going to give you a value of 0. So therefore, the delta G is equal to 0. Now, if we're looking at this graph, notice that we have a negative slope in both the forward and reverse direction. Okay. Neither one is dominating. And so when both of these lines just kind of like intersect towards this valley, this is where our equilibrium is going to lie. And if we're looking at this specific point, then we have roughly like 50-50 of reactants and products. Okay. And so overall, there's going to be a spontaneous process for some reactants to be converted into products. And there's also going to be a spontaneous process for some products to be converted into reactants. And it's going to keep on doing so until it reaches this state of equilibrium. Okay, so the take-home message that here in this case, the position of equilibrium, neither is favored. And with respect to delta G, neither the spontaneous, or neither the forward or the reverse direction is spontaneous or non-spontaneous. All right. And so, whereas here when delta G is greater than 0, we have a net shift in spontaneity towards the reverse direction, not the forward. Whereas here in when k is far, far greater than 1 and delta G is less than 0, we have like this net shift towards the right side, telling us that the formation of the products is spontaneous and the formation of the reactants is non-spontaneous. Okay. All right, so now that we've discussed this qualitative perspective of the relationship between the Gibbs free energy and the equilibrium constant, we're going to go ahead and quantify the relationship between the two. And I'm not going to go through the derivations. I'm just going to go ahead and give you guys the equation. And so here we can quantify the relationship between the equilibrium constant and the change in Gibbs free energy under standard conditions. And so under standard conditions, the equilibrium constant, or I'm sorry, if you take r and you multiply it by t and you multiply it by natural log of the equilibrium constant, then you're going to get the change in free energy under standard conditions. So let's go ahead and talk about the pieces. R, it's going to be another gas constant, but it's not 0.0821 liters, atmospheres, moles, Kelvin. Remember that delta G is expressed in terms of energy, and so therefore we're going to use the R value that has the unit of energy in it. So it's going to be 8.314. And so this value is going to be 8.314. This temperature, notice that it's in Kelvin, so we have to convert everything into Kelvin units. And then last but not least, we just take the natural log of the equilibrium constant. And so this equation actually does a lot of things for us. As simple as it is, it connects a lot of concepts that we talked about throughout this whole entire semester. And so K is an equilibrium constant, and it can represent any equilibrium constant that we've discussed. And so in terms of like problem solving, in terms of me asking questions, I can literally pull any concepts that we've covered in the past chapters and link it to delta G. Okay? And so all of your techniques in solving for the equilibrium constant Kc, equilibrium constant Kp, the acid ionization constant, the base ionization constant, Kw, K formation, K instability, Ksp, all of these different K values that we've discussed in one form or another can literally be plugged in to this equation. So it's a very simple equation, but it can be a little bit, not crazy, I wouldn't say crazy, but the calculations can be a little bit more complex just because it links up to any of these K values that we've talked about in prior chapters. All right, so we're going to go ahead and look at a couple of examples just to demonstrate its simple use, and then we'll go ahead and look at a little bit more, not so much a challenging use, but just to demonstrate how this K can be linked in to any of these K values. Okay. And so let's just go ahead and take it slow. We're going to go ahead and calculate Kc for the following reaction if the Gibbs free energy, the standard Gibbs free energy, is already given to us. And so the idea is that we're connecting delta G naught, the standard Gibbs, the standard change in Gibbs free energy, and that of an equilibrium constant. So whenever you guys see these two in one problem, and you are talking about standard conditions, then you're going to go ahead and use this specific equation such that the change in free energy under standard conditions is equal to negative RT times that by the natural log of K. In this case, we're talking about Kc, and not just any generic K. And so if we're already given this value and we know what R and T is, then we just need to perform some algebra to isolate Kc. So what I'm going to do is I'm going to divide these two to the other side. So delta G naught over R negative RT is equal to natural log of Kc. And so what we're going to do is we're going to isolate Kc by taking the anti-natural log so that we get this expression such that Kc is equal to e raised to the negative delta G naught over RT. Okay. And so all we're going to do is just plug in our numbers and put this in our calculator. So let's go ahead and start. And so notice that delta G naught is in kilojoules, right? So we've seen this plenty of times over and over again in prior problems or prior lecture videos where the units needs to match up. And so I'm just going to look at this term in the parentheses for now. So here we have negative 474.4 kilojoules per mole. Divide this by RT. So remember, R is 8.314 joules per mole Kelvin. And so this was what I was referring to, right? The energy units not matching. And so I think this time around, I'm going to just convert everything into kilojoules. And so I'm just going to change some things up. So to convert this into kilojoules, I'm going to take this decimal and move it 3 times to the left, divide it by 1,000 basically. 1, 2, 3. Okay. And so that would be my value in kilojoules per mole. Okay. And so the last thing that I need is temperature. In the problem, it didn't really state what the temperature is, but we know that we're under standard conditions. And so what must be the standard temperature that we're using? And so if you said 298.15 or 25 degrees Celsius, then you're absolutely correct. So 298.15 Kelvin is the standard temperature in Kelvin units. And so if we reduce this fraction, just plug everything in the calculator. So let's see. We have negative 474.4. Then we're going to divide it by 0.008314 times this by 298.15. I will get -1. So I'm just going to go ahead and write it down here. So Kc is equal to e to the negative 191.4. Okay. And so now that we've reduced this whole term into simply negative 191.4, we're going to go ahead and just perform this function. And so the value of Kc that I get is absolutely ridiculous at this point. I wonder if I did that right. Let me just check my work real quick. So 474.4, divide this by 0.008314 times this by 298.15. Yeah. And it's a negative value. Times this by -1. Interesting. All right, anyways, sorry, I just had to check my work. And so my Kc is going to be 7.65. 8 times 10 to the negative 84. Okay. And so if you guys look at the equilibrium constant, this value is so far less than 1 that the amount of products formed is almost non-existent, right? So if we have to calculate the equilibrium concentration, if you guys can imagine doing an ice table and calculating the equilibrium concentration, the magnitude of your concentration is really low. And so what that tells you, so one way to check our work is to look at the delta G. So if you look at the value for delta G, the value is a positive value, right? So it's positive 474.4. And so since this is a positive value, we know that the forward reaction is non-spontaneous. Okay. And if we're looking at the equilibrium constant, yeah, it makes sense. I mean, look, Kc is far less than 1. And so the forward reaction is non-spontaneous. And let's think about this concept. Like, if we look at a glass of water, if we have like pure deionized water, or it's a pure substance completely, and we let it just sit in the room at 25 degrees Celsius, it doesn't produce hydrogen gas and oxygen gas spontaneously. The only way that it can produce H2 gas and oxygen gas spontaneously is if there's some type of catalyst. Okay. All right, so this is one way that we can use this equation. And we're simply moving terms around and calculating for the equilibrium constant, Kc. And always just look back at your answers, compare Kc to delta G, and see if they are on the correct trajectory. All right, so let's go ahead and look at the next example here. So we have the molar solubility. So this question is reading, if the molar solubility of silver chloride is 1.34 times 10 to the negative 5, we need to determine the change in Gibbs free energy under standard conditions for the following process. And so the process is describing the ion of silver and the ion of chloride coming together to produce this precipitate. And so if you recall your experience in precipitation reactions done in lab, when you mix those two solutions together, I mean, it just happens spontaneously, right? And so because this reaction is spontaneous, then we should expect to get a negative delta G. Okay. And so that's something that I'm going to go ahead and predict at this moment in time, that our value for delta G should be negative. So let's go ahead and calculate this. So first we need to link up, we need to find some type of expression for delta G. So we have two expressions. Delta G is equal to delta H minus T delta S, right? And so we have the second one, delta G naught is equal to negative RT times this by the natural log of K. And so if you guys are looking at the given value, here we have the molar solubility of silver chloride. And so that is a concept from the previous chapter, which is the solubility of slightly soluble, mostly insoluble salts. And when we were going through that chapter, molar solubility is connected to Ksp. And so through that logic, we know that we're not going to be using the equation at the top to determine the Gibbs free energy under standard conditions. In this case, for us to figure out the delta G naught, we have to figure out Ksp. Okay. And so this is describing the molar solubility of silver chloride. However, if the equation that's given to us, that's not describing the silver chloride becoming soluble, it's describing the production of silver chloride. And so we can't use this specific chemical equation to figure out the Ksp value. For us to figure out the value for Ksp, we need to simulate the silver chloride becoming or dissociating to reflect the idea of molar solubility. Okay. And so when your silver chloride is your reactant and you're going in the forward direction, or if you're looking at it in the forward direction, then some amount of your precipitate is going to be soluble, which is going to reflect the idea of molar solubility or just solubility just in general. And so here we can go ahead and create an ice table, and we know that the problem didn't really give us any initial values, and so we're going to put nothing in AgCl. However, we are going to describe that some amount of silver chloride is going to be soluble to produce a certain amount of silver and a certain amount of chloride. And so the equilibrium concentration for silver and chloride is going to be equal to the molar solubility of silver chloride. And so we can go ahead and write a mass action expression, and when we write mass action expressions, we ignore the solid state. And so this is simply the concentration of Ag plus raised to the first power, because we have a coefficient of 1 and a coefficient of 1, times this by the concentration of Cl minus raised to the first power. And that's going to give us the Ksp value. Oops. And so in this case, the molar solubility, or S, is already given to us. It's 1.34 times 10 to the negative 5. And so we can figure out Ksp by simply taking the square of the molar solubility, which is 1.34 times 10 to the negative 5. And so the Ksp value, let me plug that in real quick, 1.34 times 10 to the negative 5 squared, that's going to be approximately 1.80 times 10 to the negative 10. Yeah. So that's really awesome. We figured out the Ksp value for this slightly soluble, mostly insoluble compound. Now that we have the Ksp, we're going to go ahead and plug it in to this equation right here. And so we're going to have delta G naught is equal to, actually, real quick. So remember that the Ksp is describing the silver chloride decomposing to silver ion plus chloride ion. And if you guys are looking at the equation of what we're really solving for, it's the silver ion and the chloride ion forming silver chloride. So this equation that I've highlighted in this golden yellow color is simply the reverse of the value of KSP that's being represented. And so it looks like I need to manipulate my KSP, right? So this equation and this equation are flipped. And so when you flip an equation with respect to the equilibrium constant, what do? You take its reciprocal. And so for silver ion to react with chloride ion to form silver chloride, which is what the question is asking, I would have to take the reciprocal of our KSP value. And then that's going to equal to the equilibrium constant that we're going to plug into our equation. I was hoping I'd get that arrow right in there. Just had to modify it just a little bit. So if I take the reciprocal of 1.80 times 10 to the negative 10, so it's going to be 1 divided by my answer in the calculator, that K value is going to become 5.56, nope, 5.57 times 10 to the 10 to the positive 9. So look what happens to my equilibrium constant if I flip this equation. This is telling me that the forward direction, that tells me that if I'm taking silver and chloride to produce silver chloride, the K value is going to be far, far greater than 1. That's 5.57 times 10 to the positive 9. That's way, 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 way above 1. So this is telling me that, yeah, when the system has reached equilibrium, we should expect a lot of precipitate form, which is what we observe in real life. And so here in this case, we're going to go ahead and plug in R and T. So here we have the change in delta G, or the change in free energy at standard conditions, minus 8.314 joules per mole Kelvin. And then temperature, the problem didn't really state the temperature. However, since we're under standard conditions, this is going to be 298.15 Kelvin. And then we're going to multiply this by the natural log of 5.57 times 10 to the positive 9. Okay. And so if I take the natural log of this answer to the correct number of sig figs, so here I have 2.2. So when I take the natural log of something, just remember like your pH calculations. pH is equal to negative log of whatever, the hydrogen ion, the concentration of hydrogen ion at equilibrium. And so here in this case, since I have 3 significant figures, I need 3 places after my decimal. And so overall I have 22.441. And so I'm going to go ahead and multiply that with the rest of this stuff right here. And so I'm going to multiply that by 298.15 times that by 8.3 5.314. And so when you guys are multiplying these values, this K is going to cancel out. Your equilibrium constant is unitless. And so overall, our final unit is going to be delta G is equal to negative 5.563 times 10 to the positive 4. This is joules per mole. Now, if I wanted to express this in terms of kilojoules per mole, I know that I can take a 3 out of this, leaving me with just 1. So I can do negative 5.563 times 10 to the positive 1. And then I'm going to separate that out. So it's positive 3. And this positive 3 becomes the K. And so if I express this, I'm just going to move this decimal place 1 time to the right. And so the answer is going to be negative 55.63 kilojoules per mole. Okay. So that's going to be the change in my Gibbs free energy under standard conditions. And so it's not so much, well, it is the fact that, we're able to calculate the change in Gibbs free energy. But, let's think about the concept here. Delta G naught is less than 0. It's a negative number. And so this is telling us that the reaction in the forward direction is spontaneous. So the reaction in the forward direction is going to be spontaneous. Okay. And so it makes sense, right? Look at our K value. Our K value is so far above 1. It's times 10 to the positive 9. And so we know that the equilibrium will lie on the product side. And therefore, our delta G value must reflect the spontaneity of that reaction in the forward direction. Okay. All right, and so notice how this question involves us, incorporating our knowledge of molar solubility and KSP and manipulating the equilibrium constants. That's something that we observed and talked about in the equilibrium chapter. Excuse me. And so once again, because this K value can be any equilibrium constants that we discussed, I wouldn't disregard all of the information that you guys have learned thus far. Okay? It'll play a strong role in calculating some of these more complex problems. Okay. All right, well, let's go ahead and talk about the last topic for this chapter, which is relating free energy at non-standard conditions. And so thus far we've just been saying, we're at standard conditions, we're at 25 degrees Celsius, et cetera, et cetera, et cetera. Well, not all reactions will occur at room temperature. A lot of the reactions, especially in industry that's performed, it's being performed either far, far above room temperature or far, far below room temperature. And so if we wanted to calculate the change in free energy, since we're under non-standard conditions, we are not looking for delta G naught. Okay? And so this represents standard conditions. The absence of that circle represents non-standard condition. And so the change in Gibbs free energy at non-standard conditions is simply represented as delta G, not delta G naught. Okay? And so what this equation is telling you is that it's using standard conditions as a reference point. It's analogous to the Henderson-Hasselbalch equation, where pH is equal to pK plus the log or natural log of base over acid, etc. And so for this specific equation, it's using the standard condition as a reference point, and we're just going to simply adjust the reference point based on the non-standard conditions. Okay. And so R is still going to represent the 8.314, so that's not going to change. And so T is not going to change, it's still Kelvin. But here we come across Q. And so we've seen Q kind of sporadically throughout this course. Q is going to be our reaction quotient. Where the reaction quotient is going to describe the snapshot of the relative ratio of products to reactants. Basically, we're not indicating that we're at equilibrium, so it can be any value. The one thing that I do want to mention about the reaction quotient is that to figure out Q, you do not need an ice table. So don't use ice table. The only thing that you guys will do to calculate Q is to directly write a mass action expression. Okay. And so we're going to go ahead and look at just one example, and just to kind of get a feel of how to use this equation. Okay. And so here we're going to calculate the Gibbs free energy at 450 degrees Celsius. And so already this temperature is a dead giveaway that we're not at standard condition. And notice that in the wording of the description of the Gibbs free energy, it doesn't say standard, right? So I know that this is going to be delta G, not delta G naught. And it has a reaction mixture that consists of 0.025 atmospheres of nitrogen gas, 0.075 atmospheres of hydrogen gas, and 1.25 atmospheres of NH3. And so here they gave us the Gibbs free energy at standard conditions. And so notice that this is going to act as our reference point. And so how far will our Gibbs free energy deviate from the standard change in Gibbs free energy? And so we're going to go ahead and write the equation down. Okay. So here we have negative 33.3 kilojoules per mole. And so I'm just going to go ahead and convert that to joules, so I don't have to worry about it in the future. And then I'm going to go ahead and add this by R, which is 8.314 joules per mole Kelvin. So notice that my joules match, which is what I want. And here in this case, I have 450 degrees Celsius. And so for me to get Kelvin, I just need to add 450 to 273.15. And that's going to give me 723.15. So we know that the kelvins will cancel. So the last thing that we need to do is figure out this value for Q. And so the Q, the value for Q, the reaction quotient, can be expressed by creating a mass action expression from the chemical equation. So remember, the mass action expression is a ratio of products to reactants. And so here we simply have the partial pressure of NH3 in the numerator raised to the second power because there's a coefficient of 2. And so here we have the partial pressure of H2, partial pressure of N2. The reason why I'm using partial pressure instead of like the brackets, the concentration, is because I have gas, right? And well, not only that, actually it says it right here, it's in pressure units, not concentration units. And so here in this case for my reactants, I have partial pressure of N2 raised to the first power, partial pressure of H2 raised to the third power. And so all we're going to do is we're just going to plug in these atmospheric pressure values into my mass action expression to determine my reaction quotient. And if you guys recall, the standard pressure is 1 atmosphere. So looking at the atmospheric components, we're not at 1 atmosphere. It's 0.025, 0.075, and 1.25. And so what's NH3? NH3 was 1.25. So I'm going to put in 1.25 squared, okay, because that's the value for NH3. So it says, right, 1.25 atmospheres of NH3. I have 0.025 atmospheres of N2. So I'm just going to go ahead and put that in. Raised to the first, times this by 0.075 atmospheres of H2. Oops. Okay. And so we're just going to raise that last value to the third power. Let me erase it. So all we're going to do is just simply plug this number in and see what we get. So here I get parentheses, another parentheses, 1.25 squared, end parentheses, divided by open parentheses, 0.025 raised to the first power, times this, let me do, so 0.225 times this by 0.075 raised to the third power, end parentheses, end parentheses. Okay. And so the value that I get is going to be 1.48. Times 10 to the positive 5. And so for sig figs, I'm just going to keep it to the first 2. But I'll just leave the 8 there just for accuracy. If you guys round up, it shouldn't change your answer too significantly. Well, actually it might, because you have a natural log that you're going to perform. And so I guess when you're dealing with logs, natural logs, make sure just to keep the whole number. Just mark the number of significant figures. So if I take the natural log of my answer, so if I take the natural log of this whole thing, that's going to give me 11.91. And then that's going to be the value that I replace in this term. Okay. And so if I were to rewrite this, or just, I'm going to copy and paste. So I'm just going to go ahead and put in 11.91 at the very end. Okay. So I've reduced that natural log Q to simply 11.91. Now I'm going to go ahead and multiply that by 723.15, and I'm going to multiply that by 8.314, and let's see what value I get. So all of this is going to be 7.158 times 10 to the positive 4. And so I'm going to go ahead and bring this term down. And I'm going to go ahead and plug this into my calculator. Okay. And the value that I get is going to be positive 3. Positive 3.823 times 10 to the positive 4 joules per mole Kelvin. Or, sorry, joules per mole. And so once again, I can go ahead and just move some terms around. So if I want to convert this into kilojoules, it'll just be 38.3 kilojoules per mole. Positive sign. Okay. And so basically I took a positive 3 out, and I converted that positive 3, that times 10 to the positive 3 as a kilo, and then the remaining scientific notation I just expressed. I moved the decimal 1 time to the right. And so looking at this value, here we have a positive delta G. So this is telling us that the forward reaction is non-spontaneous. Okay. So let's just take a step back and look at what's happening here. I'm just going to go ahead and copy this portion. I'm going to duplicate. I'm going to just copy it, because we need to understand what these values are telling us. So what's happening in this problem, just to clarify the concept, is that under standard conditions, so approximately 25 degrees Celsius, it turns out that the reaction is spontaneous in the forward direction. Here we have N2, 3H2 to produce 2NH3. However, if you increase the temperature to 450 degrees Celsius, according to thermodynamics, the reaction is now non-spontaneous. Okay. And so it looks like an increase in temperature, a large increase in temperature in this scenario, going from 25 degrees Celsius to 450 degrees Celsius, is going to make this reaction non-spontaneous in the forward direction. And therefore, we would need to add in, a lot of energy for it to work under this temperature. Whereas if we reduce it to 25 degrees Celsius, according to thermodynamics, the reaction will be spontaneous. Now, here, let's think about this in the real world. N2 and H2, they're gaseous, they're gas states, they're diatomic gases, and they're present in the atmosphere. So what thermodynamics is telling us is that when you have N2 and H2, the formation of NH3 or ammonia is spontaneous. And if that's true, then that means that all of these N2 and H2 gas molecules that's present in the air would spontaneously form NH3. But that's not true because that's not what's happening in real life. And so it turns out that we have to look at the kinetics of this reaction. How fast is this reaction occurring at room temperature? And so the idea of thermodynamics giving us this story telling us that the reaction is spontaneous, it is true once the reaction starts happening, but it looks like there either needs to be a catalyst to make it work at 25 degrees Celsius, or maybe the reaction rate is just really, 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 really slow at 25 degrees Celsius, but it still is spontaneous. Okay? All right, so hopefully by discussing, these concepts and pulling these things together, you guys gain, just a better appreciation for all of the concepts that we've kind of covered throughout this semester of general chemistry. And hopefully you guys gain a better appreciation of how it ties in with the fundamental concepts that you guys learned in the first semester of general chemistry. Long story short, not one specific perspective is going to give us the singular answer that we're looking for. We have to consider all perspectives, right? We have to consider the kinetics of the reaction. We have to consider the equilibrium of the reaction. We have to consider the thermodynamics of the reaction. And those pieces and more is just going to keep on layering our understanding of why certain reactions occur and why certain reactions do not occur under certain conditions. And so that's pretty much it for this chapter. The next chapter is going to be electrochemistry, and that will be our last chapter for this semester. All right, I'll see you guys later. Have a good one.